This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, so for the lab, this will be run from week 3 to week 8. Has everyone managed to register for a lab session? Yes? No? All right, so if you haven't registered for a lab session, please do. All right, I think there are limited places available, and if there are additional sessions required, we can add more sessions. All right, so please register as early as you can. I'm not too sure about this, but I think there should be about 4 labs per week. All right, and each lab can only take 6 people. Okay? So you can sign up through the central timetable. Yeah, and the lab is located on the first floor of Block D. All right, so it's known as the Walter Bassett Aerodynamics Laboratory. How many of you know where this lab is? No, none. All right. So I get this a lot as well, right? So here's a map of the Civil and Environmental Engineering building, all right, Block D 176. And I'm sure most of you have been to the engineering building before, right? So if you go through, this is Grattan Street, by the way. So if you go through the entrance from Grattan Street, you normally turn right into the sliding doors, right? And you take a lift to go up to 4th floor. All right, so beside the sliding doors, right, beside the sliding doors, there's another door which says the female toilet, all right, which also says entrance to the aerodynamics lab as well, okay? So you go through that doors, all right, you pass the female toilet, you go up the stairs, all right, and the lab is somewhere here, okay? If you look at the red point here, all right, it's somewhere there. But no worries, I'll show you how to get there again when the time comes. Okay. Right, and there is of course a lab report, okay, for this F4 lab, and it has to be done in groups of 2. Okay, so if you haven't got any partner, all right, it's good to find a partner to do this lab report. Only groups of 2. No groups of 3. So it's either you do it alone or groups of 2. Okay? Right, regarding the assignments, so regarding the lab report actually, yep, that has to be handed out 3 weeks after you attend the lab. Okay, and please do not plagiarize your lab report. Okay, so in the olden days, all right, when assignments were handed in manually in paper, all right, the tutors have to go through each assignment and check whether there's any plagiarism, right? But now everything's submitted via the LMS, right, via online, right, and instantly the software detects if you have plagiarized an assignment, okay, because it then checks your assignment with other assignments which have been submitted before, not only this year but in previous years as well. So we have a database of assignments which it will be correlated to. So please do not plagiarize. And if you plagiarize, you are going to give me a lot of problem as well. Okay? So please don't plagiarize. Right, so tutorials, all right, there's no tutorials this week or next week. They only start in week 3. Okay, and you only have to attend 1 tutorial per week. Okay, so only on the 12th of August, you'll have your tutorials, and we'll start with 5 potential flow tutorials, and then another 5 compressible flow tutorials. Okay. And as I mentioned, there's an assignment for each unit. I will give you your potential flow assignment around week 3. And if I've completed the assignment a bit earlier, I will try and give it to you on week 2, so you have an extra week or so to work on your assignment, right? And the compressible flow assignment will be out in maybe week 9. Okay? And again, assignments are to be completed in groups of 2, right? So this makes marking for us a bit easier, and also for you, I guess it reduces your load a little bit, and it allows me to, I guess, give you a bit more challenging questions in the assignment as well. Okay, is everything clear so far? Are there any questions?
Previous slides where you show us where the lab is.
Lab.
About the,
Where it is?
no, I think the next slide.
Oh, this one?
Yeah, this one.
Yeah. So don't worry too much. Everything will be online. Okay. In the lecture recordings, and I'll also upload these slides once I'm done with the lectures as well. Okay. Yep. Okay. So another thing which I think I sent out an announcement last week on Friday was the MATLAB sessions. So how many of you have not used MATLAB before? All right, so a couple of you. So I would recommend you to attend the ramp-up sessions, which I emailed on Friday. If you have not registered, I don't know whether you can still register for it though, but I think it's good to attend those MATLAB sessions. So it teach you a little bit about what MATLAB is and how do you use MATLAB. All right, on top of those sessions, okay, we will be having our own workshops as well, MATLAB workshops. And this will be available from week 3 to week 5. Okay, so currently there are 4 slots, and all of them will be held at EDS 5 in Old Eng. Okay, so these MATLAB sessions are, it's not compulsory, all right? So it's up to you if you want to attend them or not. But it will help you in your potential flow assignment, all right? So that's a big hint there. So you probably want to attend these sessions. Does everyone have MATLAB on your computer? Yep. No? Do you all know that you all can download MATLAB for free? Or are you all using cracked versions of MATLAB? Okay, good. No one's using cracked versions of MATLAB, right? Okay, good. I'll just show you briefly if you don't know. So I did a quick Google student software, all right, and you should be able to see this page here, right? So there's a lot of available software which you can use, all right, as students of University of Melbourne, and you can download them for free. So some of which are Mathematica, which is pretty good, MATLAB, right, and Microsoft Office, so for PowerPoint, Word, Excel, right, and also Microsoft Windows 10, right? So please don't download illegal software. You can get them free from the university website, okay? Okay, so lecture notes will be on the LMS. Okay, and my lecture slides will be quite similar to the lecture notes, right? And the lecture notes, which we have uploaded online, that will be probably the main reference for you guys. Okay, and I will eventually upload these slides on LMS. Okay, any questions before I start? Yep.
You know when is the rough timeline that both particular sessions will be advertised on the website?
Sorry, say again?
Those particular lab times that we can reserve on.
I think it's already on your timetable, right?
Yeah, because particular sessions are limited.
Yep.
Like for those who aren't able to be registered for particular classes, like for example, they are particular 1 and 2, so we have another for that, right? For potential university that. So is there any more particular sessions that we can sign on?
So you're talking about the MATLAB sessions or the Airfoil lab?
The Airfoil lab.
Right. So are you able to sign up to the Airfoil lab, or is it all full?
It's not full. There's no options there, so I'm only able to sign up one lab session available. Not sure. Yeah.
Oh.
Same for me.
So you can't. So practical 2 is the Airfoil lab, right? And you can't sign up for that?
No, crack one. I can sign up.
Okay, so Prac 1 is the airfoil lab, right? I'm confused now. I gotta check. Hold on a second. Sorry, I'll just double check here. All right. So you all know this website, right? To check your timetable. Oh, you can't see. Small. Ah, okay. So this is the timetable for this subject. Right. So are you all able to sign up to these sessions? Is this the one that you can sign up?
No. This is the general timetable we given to EC, but we have our own timetable that we need to register the class on in order for us.
Yep. So can you sign up to this old eng? Is it the old eng which you can't sign up, or is it this departmental organized venue which you can't?
The first one.
Oh, the first one. So you can't sign up for this.
Yeah. First.
Oh, okay. Yeah. So if you can't sign up for that, don't worry too much. Just attend the lab and see how it goes. Yeah, because it's not compulsory. So some students might have signed up, but they might not attend. Does it make sense? I think you can just walk in. Yeah. But anyway, don't quote me on this. I'll get back to you on Wednesday. All right, I'll just double check again on Wednesday, because these sessions are not compulsory. Right. So this all engineering, right? If you're registered in this all engineering EDS 5, these are your MATLAB workshops, which will help you in your assignment. Okay. Whereas these departmentally organized venue, these are your airfoil lab. Right, and everyone should register for at least one of these. Is it? Okay. Yep. I'll get back to you again on Wednesday, and I'll see. Yeah. Normally we have only 4 sessions, and that's it. But I'll have to talk to the tutors and see whether we can get more sessions for that. For these ones, right? For this.
No. I'm not referring to the
Sorry?
I'm not referring to the lab. I'm referring to the lab sessions.
The F4 lab. So it's so it's this one then. Departmentally organized venue. You can't sign up to one of these. This one.
Can you switch back to the PowerPoint slide?
Yep.
Regarding on the potential and aggressive flow lab.
Which? This one?
Yeah.
Yep. So the lab times, so these are your F4 labs.
Yeah, therefore, yes.
Yep.
We need to actually sign in our central timetable in order to enroll.
Yep.
And so when I get to choose the time session, there's none of that.
Okay, so for the F4 lab, right?
Yeah.
Okay. So sure. Yep. I'll check with Carol about this, and we'll try and perhaps you'll have more lab sessions per week, or we might extend it to week 9 or something. Right. Okay. Thanks for letting me know. Yep. Okay. I'll definitely check that out. All right. Okay. Everyone else okay so far with the subject? Yep. All right. So I'll probably start then with some materials. It's going to be a bit light today, so don't worry too much. First of all, these slides are prepared by Professor Nicholas Hutchins, right? And credit goes to him if these slides are good or bad, all right? Okay, so the purpose of this subject, right, is basically we want to predict the flow patterns, right, and the forces which occur when we have a solid body in a flow, right? So let's say, for instance, I have an airfoil, right, and I put this airfoil in a flow. I would like to predict how the flow over the airfoil would look like, and I would also want to know what are the forces acting on this airfoil, right? So what's the lift acting on this airfoil, which is very important if, let's say, you're designing an aircraft, right? You want to know what's the lift generated by the wings of the aircraft at cruising speed, for instance, and that will tell you what's the payload that the aircraft can carry, right? And also with lift, you would also have drag as well. Okay, and I think in your previous fluid dynamics course, if you studied at the University of Melbourne, this is something that we have not done yet. All right, and in this subject, we will be looking at a flow over an airfoil, right, at subsonic speeds, right, for potential flow. And it's quite nice because at the end of potential flow, you'll be able to predict the drag lift for a flow over an airfoil, and then in compressible flow, right, you'll be able to predict the drag lift and all other associated forces in a supersonic flow, right, in a compressible flow, which would be quite different, right? So the equations which govern the motion of fluid look something like this. All right, has anyone seen these equations before? Yes? Do you all know what it's called? It's written there. Yeah, it's the Navier-Stokes equation. All right, it looks really massive, right? But don't be scared by this equation. It's basically not too difficult, right? The understanding of this equation is not too difficult. Okay, and just a bit of background with this Navier-Stokes equation. It was found by Sir George Gabriel Stokes and Claude Louis Navier independently. So while these equations describe the flow, right, they actually do not have simple analytical solutions, right? Basically, it's really difficult to solve these equations because it's highly nonlinear, right? Right, and if you can solve this Navier-Stokes equation, I will give you $100,000. Okay, right? Because this Navier-Stokes equation is one of the 7, I think, Millennium Prize problems, where if you're able to solve it, I'll give you $100,000 and I'll get $1 million for solving it. All right. But yeah, so basically until now, this equation has been around for hundreds of years, but even until now, it's still unsolvable. So it's really difficult to solve these equations. Right. So engineering approaches, all right, which you can use to try and predict the flow, right, and the forces can be divided into 3 components, right? You can be analytical, all right? You can conduct some computational simulations, or you can run some experiments, which you will be doing in your airfoil lab, right? So in the experimental method, basically what you do is you test scale models, right? So here we have a model of the Airbus A380, right? And this is in a facility, wind tunnel facility somewhere in France, I think, owned by Onera. And to generate the flow, right, over this aeroplane, right, you need a large fan, right? You need a large fan to generate this flow over the scale model. And just to show you the perspective, right, of how large this fan is, here is a man standing, all right, and holding one of the blades, right? So you can see that you really need a large facility, right, a large fan to generate this flow, right? And all of this is going to cost a lot of money. You need a large fan, you need a large facility, right? You can see that this is a huge facility, a wind tunnel facility. And there's all this power supplying the fan as well, the facility. So it's using massive amounts of energy, right? And experiments are therefore very expensive to conduct, right? Scaled laboratory experiments are expensive to conduct. Right, so another option, another engineering approach is to conduct numerical simulations, right? So basically solving the Navier-Stokes equations numerically using computers. Okay. Right, so here's an example of a result, right? A computational simulation result. So if I play this. Right, and we are looking at the streamwise velocity, the contours of streamwise velocity. So here we have, just pause it for a while. Right, we have fluid moving from left to right, and this is a backward facing step. Okay, and you can see that the high velocity is in pink and the low velocity is in blue. Right, and you can see this turbulent shading and the flow separating at the back of the backward facing step, right? Okay, and these kind of simulations are really expensive. Okay, so to conduct this kind of simulation, right, first you have to discretize this problem, all right, this domain. So you have to break it up into small parts, which we call it cells, all right? And in each cell, right, each of these small cells, we're going to solve the Navier-Stokes equation, right? So it's going to be very, very expensive to do that numerically. Okay, and this result which I've showed you is probably only representative of a small part of an airplane, right? So a really, really small part. Okay, and if you want to simulate the whole airplane, all right, you need a computational power of about 10 zettaflops. And to put this in comparison, right, a computer that you have, your desktop computer, right, let's say an i7 computer, it's about 177 gigaflops, right? So it's about 10 to the power of 9. Now you have i9 Intel processors, you have AMD Threadripper and all that, but it's still about 10 to the power of 9, power of 10, okay? And even the fastest supercomputer that you have at the moment, right, is about 33 petaflops. Okay, so this means that we are still very far away in simulating a whole aircraft at operating conditions. Okay, and we are going to need a lot of computers, right? But according to Moore's law, right, you all have heard of Moore's law? Yep. So it is expected that computational power will double every 24 months, every 2 years. So maybe in the future, right, we will be able to simulate a whole aircraft. But at the moment, we are not able to do that. Okay, and definitely that's not what we're going to do in this part of potential flow. Okay, so the path which we will be taking today, or in this subject, is the analytical route. Okay, so basically we are going to start with the Navier-Stokes equations, but we are going to make some simplifications, right, so that we can solve it using a pen or paper, or just solve it using your laptop, right, or desktop. Right, so this is the Navier-Stokes equation, which you all have seen. Can anybody try and guess what this equation, what this equation is? Exactly, right? So it's continuity. Basically, it's the conservation of mass, right? So mass cannot be created nor destroyed, right? And if you have a control volume, right, continuity basically means whatever is coming in has to come out at the other end, right? So that's continuity. How about these equations here, these massive ugly equations? Exactly, right? Conservation of momentum. All right, so don't be afraid of these equations. It's basically just continuity, conservation of mass, and these are just conservation of momentum, linear momentum, right? In the x, y, and z. So basically these equations are just F equals to ma. Okay? Now let's have a look at the different variables that we have here. So you can see that there is t here. Okay? And this is basically time. Okay? So if I look at this term here, it's just saying that there is a change in density with time. Okay? And these other terms are the change in velocity with time. Okay? All these terms at the bottom here, that's basically your coordinates, basically, right? So x, y, and z are your streamwise, normal, and span-wise direction in a Cartesian system. Okay, so if you consider a fluid element, right? This is just some fluid element, right? I can write my coordinate system as x, y, and z using the right-hand rule. Okay, and x is the direction of the main flow, basically. Okay, of the principal flow. So the terms u, sorry, not the terms, but the variables u, v, and w, okay, these are basically just your velocities in the x, y, and z direction. So u is basically in the x direction, okay, and your velocity v is in the y, and w is in z, so on. Okay. So rho here I've already mentioned earlier, okay, and rho is your fluid density. Okay. So if you have a fluid element, okay, the force acting on this fluid element is F equals to mg, right? And density comes in the mass part, right, in m, where m equals to rho v, right? Your density times your volume of the fluid element will give you the mass. Okay. And here we have P, right? I hope you all can differentiate between rho and P. Okay, it looks very similar, but they're not. P is pressure, right? And if I consider a fluid element again, and if I look at the YZ plane, all right, and I consider some pressure acting on that YZ plane, there's going to be some other pressure which is acting on the surface at the same surface, sorry, at the XY plane, some X location downstream, right? And that's going to be my pressure plus some change in pressure. Okay, and pressure is always acting on the surface. Don't worry too much about this. We'll go through the equations a bit later. Okay. Right. Now on the right-hand side of the momentum equations, we have these terms here. Can anybody guess what these terms are? Yep. That's right. It's a tensor. All right. There's 9 terms, so it's a tensor. But what is tau? What is? Yep, shear stress. Correct. Right. And I believe that you might have seen shear stress in your previous fluids course. Right. I think when you were working with the pipe flow problems, you're looking at the pressure drop, the major losses, right? And the major losses is due to the shear stress, right, of the pipe. Okay. So your shear stress, all right, is basically just equals to your viscosity times your velocity gradient. All right. So if you have some shear stress acting on the fluid element in the x direction, right, your fluid element is going to deform. Okay. And this will give you a strain rate. Oops. Right, and this will give you a strain rate of psi. Okay, and this shear stress is known, the notation of it is just tau yx, right? Because you have a strain rate in the y direction due to the shear stress in the x direction. Okay? So this viscous stresses, okay, only occurs when you have viscosity, right? So when you have a Newtonian fluid, right, the viscous stresses is just mu, your viscosity, times the velocity gradient. Okay? But if you have inviscid fluid, right, a fluid with no viscosity, you do not have these terms here. Okay? Right, and also again, if let's say I have a shear stress acting on the y direction, I'm going to have a strain rate in the x due to the shear in the y. Right, so I'm going to get x tau xy. And as one of your friends mentioned, it is a tensor, right? So you have 9 terms. Okay. All right. So we're going to start, I guess, trimming down this equation a little bit so that it's a bit more manageable. So the first thing we want to do is we want to consider a 2-dimensional flow. Okay. Did you all see that? Too fast. All right, so in 3-dimensional flow, if I have a particle, right, the particle can move in in all x, y, and z. Right? It can go everywhere in that domain. Okay. However, if it's a 2-dimensional flow, right, and let's say I'm going to make the flow 2-dimensional in the x and y coordinates, right, then my particle is going to be confined to a plane, this x, y plane, right? And basically, the flow is going to be same at all z locations. It's basically invariant in the z because it's a 2-dimensional flow. Okay. So again, going back to our flow in airfoil, all right, if you're assuming a 2-dimensional flow, it basically means that the flow at all z locations are the same. And this is actually, I guess, quite a reasonable assumption, right? If you're assuming that your airfoil does not have any tapering, right? It's all constant. It's quite a reasonable assumption to make. Okay. So if I assume 2-dimensional flow in the x and y plane, which terms do you think I can cancel? Sorry? Z? Did I hear Z? The Z terms? Yep. Exactly. Right? So all the Z terms can be removed. Okay? So in continuity, this goes off. Right? All these other terms goes off. Okay, and because it's only a 2-dimensional flow, I do not have to solve the momentum in the Z, right? So everything goes off in the last row. So makes it a bit nicer. Okay? Now, you're going to look at the viscous terms. Okay, and as I mentioned before, when you have viscous stresses, right, your fluid will deform. Okay, and you'll form some shear strain rate, right? Fine. So I'm going to show you, I guess, or I'll try to explain to you the differences when you have viscosity and no viscosity. Okay. Wait, but before that, does everyone know what viscosity does to the fluid, or what the viscous terms do to the fluid? Anybody want to guess? Friction, yes. Yep, I guess friction is because you have a no-slip condition, right? Anything?
Boundary layer.
Yep, exactly, right? So when you have viscous stresses, you're going to form a boundary layer, right? Because of the no-slip condition at the wall. Okay? So, but basically, I guess, these viscous stresses, they like to diffuse, or they like to smooth things out. Right? It acts like a high-pass filter. It likes to smooth things out. Okay? So This is just a thought experiment, all right? Where I've broken up my fluid into small elements, right? Of course, a fluid is continuous, but I've just broken up into small fluid elements here just for illustration, okay? Right, and if let's say I apply some velocity to the first 1, 2, 3, 4 rows of fluid elements, okay? And this red line here is basically my velocity profile, right? So at the start, my velocity profile is 0, okay? And for a inviscid or for a fluid with no viscosity, when I apply this velocity to the first 4 rows of the fluid elements, you can see that I have a big jump, right, in the velocity, okay? And the other fluid elements below it doesn't know anything about what's going on above, right? Okay, so it's not able to transfer any momentum, all right, to the fluid elements below. Okay. Now, if I have a viscous fluid on the other hand, right, and if I do the same thing, right, I apply a force or I apply a velocity to these 4 rows, what viscosity would do is it would transfer some of the momentum, right, to the fluid below. And I'm just going to play it again, right? So look at these fluid elements. It's moving and it's also deforming, right? As you can see here, yep. Right, and because of viscosity, you are forming a shear layer here, right? And momentum is transferred to the other fluid elements below as well. Okay, right. So I guess most of you know what a fluid with high viscosity is, right? It's like honey, right? Oils, and fluid with low viscosity would be, I guess, water or something else, right? So I have this. I don't know whether I've explained it well, but here's another experiment, right? A very easy experiment, which would try, I guess, to help you understand the differences in fluid with high viscosity and low viscosity. Okay, so initially we have a container with high viscosity fluid, and it's initially at rest. Okay, and we have a float here, which will be placed into the container, into the fluid. Okay, and this container is going to rotate anti-clockwise. Okay, so you can see that he has dunked the float, all right, into the fluid, and you can see it's quite thick. It looks like some kind of honey or oil. All right. Okay, so he has placed this float here, and he's going to rotate the container. Now, I just want to ask you, do you know what's the velocity going to be at the wall? The velocity of the fluid very close to the wall. When it rotates, it's going to be 0, right? So it's going to be rotating together with the container, correct? Yep. And because this is a very high viscosity fluid, what do you think will happen to this float when it starts rotating? It will? Will it rotate together or will it not rotate together with the container? It will rotate together. Okay, let's see. Right, 50-50. Okay, right? So it rotates together with the container, right? Because momentum from the walls, right? Or the walls of the container is immediately transferred. Okay? And when it stops, the float stops together. And when you start it back, it moves again. Okay? Oops. All right. Now, on the other hand, a low viscosity fluid acts a bit differently. Okay? So this time, again, I have a float, right? But this time the float is placed in a low viscosity fluid. Okay, so he dunks it in, and you can see that it's pretty low viscosity, right? Looks like water. Okay. Now, if he starts rotating the container, what do you think will happen with the float?
Stay still.
It stays still forever? Okay, let's see what happens. Right? So when you start rotating it, it stays still, right? But after a while, you can see that the float starts moving. Okay, and it's because the momentum from the walls of the container is being transferred, right, to the inner parts of the container, right, due to viscosity. So because it's low viscosity, momentum is transferred a bit slower. Okay. Right, and when it stops, the float still moves around. Okay. Yep. So here's another similar example, right? But this time we have put some dye, right, in this fluid here. Okay. You can see that it's a line drawn fluid. Okay, and let's see what happens when we rotate the container. Right, you can see that the line remains straight. Okay, that's why when we place our float, it moves instantly, right? But now if you compare it with a fluid with low viscosity, okay, so you can see that the dye at the wall of the container follows the container because of the no-slip condition, right? And then slowly momentum is being transferred towards the center. Okay? Right? So very close to the wall we have regions of high shear, okay? But far away from the walls of the container, you can see that there is not much velocity gradients happening there. Okay? Right, so if you go back to this example, okay, so at regions of high shear, right, so at this point here where there's high shear, okay, viscosity is very important, okay, the effects of viscosity is very important. But if you look at regions below, okay, or regions above, which has very low shear, okay, the inviscid approximation is actually not too bad. Okay, we are not so affected by viscosity at regions where there's low shear or no shear, right? Okay, so we are going to consider inviscid flow. So we're going to ignore this viscous terms, right? So which means that you will not have a boundary layer forming, okay? Right, so if we neglect the viscous terms, okay, it means that we are neglecting the prospect of flow separation. Okay, so if let's say I have a cylinder here, okay, and I have some flow which is moving from left to right, all right, you can see that the flow is symmetrical, right? So basically the flow is going from left, it goes over the cylinder, and then it comes back, okay? It reattaches again to the flow. And you look something like this. So this is a creeping flow, so basically a very, very, very slow or low Reynolds number flow, a creeping flow. Okay, and you can see that the flow reattaches again. Okay, but this is a bit concerning because most engineering flows are at higher Reynolds number, right? And in real life, right? This is not going to happen. This potential flow solution is probably not very realistic. Okay, if I look at the drag or the forces acting on this cylinder, what can you tell me about the drag or the forces acting on this cylinder? It is? How's the drag at the front and the back? How does it look, or how does it compare? It's symmetrical, right? So if it's symmetrical, it basically means that this cylinder has no drag, right? But that's not realistic, right? So if you go for a jog, right, you know that there's some drag acting on your body, right? So this result is not realistic, basically. Okay, what actually happens is that you'll have flow separation, right? You look something like this, where it is initially attached to the flow, but then later on flow separates. Okay, so this is what would happen when you have a flow over a bluff body. Okay, and the pressure distribution looks something like this, right? So for bluff bodies, right, such as a cylinder or a sphere, the effects of separation, they are very important. Okay, and as I can show you here, this is a flow over a cylinder. You can see that initially the flow is attached, but then at some azimuthal angle, at some angle theta, sorry, you can see that the flow separates, right, and it's turbulent behind. There's a turbulent wake occurring. Okay, so our assumption of inviscid fluid is probably not very good for a cylinder, right, which is a bluff body. How about a streamlined solid body such as an airfoil? Okay, so an airfoil is a streamlined body, all right, and you can see that the flow over an airfoil looks quite nice for a potential flow solution, right? And if you compare it with an actual flow, all right, you will have some separation, right, for a flow in an airfoil. But for streamlined bodies, the effects of separation is relatively minor. Okay, so the assumption that the flow is inviscid, I guess, is quite reasonable for a flow over an airfoil, right? Yeah, so I think I'll leave it at there for today, right? And on Wednesday, we'll start chopping off more terms, and we'll continue from there, right? Thank you.
Please upload the notes before so we can comment.
I'll try and do that. Yeah, I'll try and do that. But the lecture notes are there.
Yeah, but they are not similar.
I think they are pretty similar. No?
Is it this one? Because I downloaded this, but it's not similar.
Yes, this one. Oh, is that? Oh, okay. I'll try and.
This one is not 70. The assessment is not the same.
Yeah. Don't follow the assessment a lot. But the material is the same. The content is.
It's there.
Yeah. So we're going through about this.
Yeah. Thank you.
Yeah, but I will try and upload if I have the time.
Thank you.
Okay. Alright.
Which version does the MATLAB use? Doesn't really matter.
Yeah, I think 2018 is fine.
Mac or Windows? It doesn't matter.
I think it's okay. I think Windows or Mac should be okay. Yeah.
Windows or why
I would say I think any would be okay. I think it should be fine.
Okay.
Yeah, I think it should be compatible for both. Yeah, should be alright.
Thank you.
Okay.
So I didn't select Prac 1, so it's okay. Just go to the AT lab.
Wait, what's Prac 1 again?
It's here. The same question was made. So I think this is the lab you were talking about.
So this is Prac 2 is your airfoil lab.
Yeah.
So Prac 2 is the
This is the
important
6
one.
people one.
Yeah. This is the important one.
You have to sign up with Prac 2.
Yeah,
Yes.
I got it already.
Okay.
I can
Yeah.
sign in Prac 1.
Oh, okay.
So it's
Yeah,
like
so it's the-
tutorial stuff.
Yeah, that's the MATLAB workshop. Yeah, I'll try and increase.
So Prep 1 is med-level shop.
Yes, which
It's
is
not compulsory.
Not compulsory. Yeah. But it's advised that you go because we'll be helping you with the assignment.
Oh, okay.
Yeah.
Thank you very much.
Alright, okay, no problem.
Professor,
Hey.
it says like right here it says like one weekly 120 minutes practical one and one weekly 120 minutes practical 1 and 2. So in my case, like I've registered practical 1 and 2, so
Okay.
I'm all set.
Yes, you're all good.
And is it weekly?
No.
it's
So
just,
practical 2, right? So it's 18. If you click,
Okay, that says 18 right there.
can I check?
No, just that's it.
Oh, that's it?
Yeah.
Okay. 18, Okay, I'll check it
What
out.
does it mean 18?
So it's session 18, so you only have to attend it once.
What do you mean 18?
So you should only attend it once, I think.
So it's like my session is at the 18th.
Yes. So I will put out an Excel.
So like somebody has like number 1, number 2, number 3, and in my case that's 18th.
Yes.
Okay.
I'll probably, so it's probably not week 3, it's probably week 7 or 8.
Okay, well that's way back.
Yeah, a bit later, yeah.
Okay. Okay, I see. What about this practical one? You just said that it's not compulsory.
Yes, it's not compulsory, but I highly recommend you to attend
Okay.
for the potential full assignment.
Okay, so
that's running
so in my case, I will be in group 4.
So for the pracs, right, there's only 4 sessions.
Okay.
So it's 1, 2, 3, 4. Yeah.
Okay, I see.
Yep.
Thank you very much.
Okay, no problem. Hey, yep.
So I'm not able to add. Basically, it seems all of the lectures are full for practical 2 as well as practical 1.
Practical 2 and 1 is full.
Yeah,
2 and 1.
2 and 1. Practical 1, not registered. Practical 2 also it's saying no classes registered. And when I press on the option, it says, wait, it is saying practical 1 now.
Is it?
But it's clashing with. No, what is this?
Practical 1.
It's unavailable. Everything is unavailable.
Are you sure?
Yeah. When I'm clicking, it says unavailable. So what can I do regarding practical 1?
So I'll probably contact Carol and I'll ask her to increase the slots for practical 1. Practical 1 is the F4 one, right?
No, so as far as I've read the system subject information guide provided on LMS, practical 1 is the optional thing for MATLAB. And practical 2 is the
F4.
lab.
Okay. So you can't register for both?
Both. Yes.
Okay. Yeah. Okay. I'll probably send out an announcement or I'll inform you on Wednesday.
Okay.
Yep.
So basically, there's no need to panic. Right? It'll just
Yeah.
pop up in the timetable as and when I can add them to the timetable. Right?
Yes. So I'll probably try and get it done soon. Yeah. Do you know Carol?
No.
Carol's on the 4th floor of the engineering building.
Okay.
So might be good to email her to discuss all this. But never mind.
1 second. So.
She sent an
Is-
announcement.
is-
Yeah, that's her. Yep.
Okay.
She might be good too.
She said that there will be more sessions open next week, but the next week is already started today.
Okay. Yeah, so she hasn't opened it yet, I guess.
Yeah. So it says next week, but that was the last week.
So it should be this week, right?
Yeah, it should be this week.
Yeah. I'll probably remind her because she's quite busy with other subjects as well.
Thank you so much.
Okay, no problem.
就是 Everflow Lab 就是做完那个结果，然后下一就是做这种三角上去了。我现在只是查看这个。可以不用去的是吧？就是还有他别的地方也没码的，也没码。
想回家吃饭。
啊，真的啊？
就我一个人，
然后就不交了。
他把那个扣的什么